Hey folks, as we are nearing the time that we're going to submit the paper describing this toolbox, figured it might be nice to create a little demo video here just giving you a brief tour of our toolbox. So this is the DeLINEATE toolbox for deep learning in neuroscience. Don't ask me exactly what it stands for because oh, there it is. The deep learning in neuroimaging, exploration, analysis tools, and education. So here's your education in this video. And technically, you don't have to use it for neuroimaging, but that's what we mostly use it for. So anyway, let me just give you a brief tour of how you might use this if you're getting started now. What I'm going to do here is actually just copy the link to the toolbox, and I'm going to open up a terminal window here. Just move this out of the way. Make a temporary directory for it. Just download, because I'm a nerd, with the command line I'm going to download it, but you could just click the download link if you were a normal human. Unzip that. Now this is on my local Mac here, which I do not have a video card that can be used for GPU accelerated analyses on. So we're just going to look at the code and stuff here for now. I'm looking at version 0.2 beta of the toolbox, but this should be reasonably similar for future versions as well. So we're just going to look at the code and stuff on here, and then I'll show you on our analysis machines with the good GPUs how this thing actually runs. So if you download the toolbox, you'll get, this is the release version. There's also, you can get kind of, the Git repository if you want to get every single commit we do, but if you want the release version, here it is. You can see there's just a handful of Python files in the main toolbox. And if you are not a programming type person, if you just want to use the toolbox, you don't actually have to interact with these two directly for the most part. You're actually going to be mostly interacting with job files here, which are JSON files, which JSON is JavaScript object notation, I think, and that's a kind of text format that lets you express relatively complex data structures pretty easily. And the way we have it set up is you can actually create these JSON-based job files that let you configure an analysis without having to write a ton of your own Python code. So we have some samples here that I will just give you an example of. I have a nice little, for the Mac, I really like this JSON editor program here. It's like $3 or $5 or something like that in the App Store. I highly recommend it because it lets you edit your JSON file in a structured way. So if I kind of flip through, I can see kind of the components of this JSON file. Now the real JSON file is only a text file. So if I want to actually see the text that's in this file, it looks something like this. So if you're writing it just by hand in a text editor, that would also be fine. You just have to make sure you ensure JSON compliance, which is one reason why it's nice to use a graphical editor, because that will kind of make sure you get the format right yourself. But basically, it's a little crazy looking at first before you get used to it. I'm going to skip over the model and just show you some of the other stuff. So probably the easiest thing to specify in this little data structure is the data parameter. Which is here it's a structure that in Python we would call a dictionary. The whole thing is a structure that in Python we'd call a dictionary. And inside data has a subdictionary. If you're not a programmer type person, you don't have to worry about this too much. The main thing to note is that the data bit of our job description has two sub bits to it, one of which is called files and one of which is called loader. And at least canonically, these would be used to specify a loading function, which you may have to write yourself in Python if your data has a format that we are not prepared to load in. But we have a few sample loaders for you, and they're usually pretty short and easy to write. And you might be able to get by on the sample ones we provide. And then you also specify what files you're going to load in. So this is like wherever your data file is going to be located. And this can be an absolute path name or a relative path name, relative to where you plan to be running it. So that's one of the things you're going to need in order to run analysis is some data here. one of the other main things you're going to need, and this is the more complicated looking thing, but it's probably the next one to talk about, is your model. So you can actually run either PyMVPA or deep learning analyses with this toolbox, but this is a deep learning analysis. It uses the Keras, Keras, like that, the Keras toolbox as its backend, and then that in turn has various backends of its own. If you don't know anything about deep learning or neural networks or whatever, don't worry about this stuff too much. The main thing to note is that there are various options you can specify that are sort of generic options for the model, and then you can specify a number of layers, right? So if you know anything about neural networks, basically you have a number of layers of artificial neurons to pass your processing through. And basically what we're doing here is describing the parameters of each layer. So you start out with an input layer, and this is basically a list, or an array. This indicates kind of the beginning of a list, and it's an array of little dictionaries where each dictionary describes a layer. So what we basically got here is an input layer that essentially reshapes the data a little bit just to get it in the right shape for the next layer that's going to be coming up. It has a shape of 18 by 273 because this is EEG data with should be 18 electrodes and 273 time points in each trial. And it's going to reshape that into 1 by 18 by 273, which is not too big of a deal. It just adds kind of a null first dimension because that's what our convolutional layer is going to be expecting. So the next layer is this convolutional layer. Conv2D is the layer type. Again, if you don't know much about neural nets, that's for another time. Basically, we're going to define 12 convolutional filters. They each have a shape of 3 by 6. You can set things like regularization. So this has like a little bit of L2 regularization on it. And a padding type, which is something you can specify for most kinds of digital filters. So this basically says we're going to have a layer that's a convolutional layer of our neural network that defines 12 convolutional filters of size 3 by 6. After that, that's going to move on to a leaky ReLU layer and a whole bunch. We got some other stuff going on here that we don't need to get into. Batch normalization. We're going to flatten that stuff. Then go on to a series. Actually, no, I take that back. Just one dense layer here. Another leaky ReLU dropout. So dense layer would be kind of your classic, just kind of run-of-the-mill neural network layer that doesn't do any convolutional stuff or anything. It's just like a perceptron type layer. And so that goes through some leaky ReLU, dropout, batch normalization. But anyway, you end with an output layer, which is again another dense layer that has 3 units. So you need 3 output units because of the 3 category classification. Again, if you don't know anything about neural nets, this is all just gibberish to you. But the basic point is that this describes a somewhat relatively simple but still kind of complex neural net. But you don't have to write a bunch of Python code. You just have to know the names of the parameters, which is not nothing. But this is probably easier than writing a bunch of Python code because if I want to change some of this stuff, I can just jump in here and change some of these options. And remember, if you have a graphical JSON editor, you can just kind of go in here and think of it maybe an easier way where you go in and say, okay, let's flip down my other things. But my model has a bunch of layers in it. Layer 0, if I expand this a little bit, layer 0 looks like this. It has an input shape of 18 by 273. Layer type is named reshape. Target shape is 1 by 18 by 273. So you can go in and kind of edit all these things graphically if you have a good editor app for this kind of thing. Anyway, so going back to the actual JSON though, because a lot of us are just going to be using the text form of this. So you need some data, you need a model, and then you need to specify some attributes of your analysis. So things like nits, which is the number of iterations to run, because there's usually some randomization involved. You want to run your analysis multiple times to get good estimates of its performance. We have a number of different cross-validation types you can run. This one's what we call loop over SA, which is basically SA is a sample attribute, and one of our attributes of each of our samples or trials of data is subject. So what we're going to be telling it is to loop over subject, and we're telling it to loop over the sample attribute subject right here. And what this means is we're going to basically run this model separately for each subject in our experimental data set. We also specify things like our train validation and test data set ratio. So this basically means 70% of the data will be used for training data, 15% for validation, 15% for test. Don't worry about scaling right now, but you can rescale your data various ways. What we're going to classify over is another sample attribute named category, because basically this is a task where people were perceiving either faces, scenes, or objects, and we're just going to try to classify which one they were looking at based on their EEG data. And then there's a few back-end options that are kind of specific to, in this case, Keras. And this has to do with basically like how soon Keras decides its model is good enough and a few other things. So again, don't worry about that if you're not already a deep learning person. And then lastly, we have something that should be pretty straightforward for most people. Just basically specifying what kind of output you want to spit out, what the output location is, which again is a relative path relative to wherever you run the script from, what you want the stem of your output files to be called, and then what output file types you'd like. So there's a few different output file types you can ask for it to give you. One is an accuracy summary, and then you can get output for every individual score and every individual label of whatever you're trying to classify. So this is if you want to see exactly how well your model did on every single item in your test data set. You can see the individual classification scores and class labels for every single trial or sample in your test data set. And you can do whatever you like with those. And also one thing we like to do sometimes is spit out a copy of this job configuration. The only reason we want to do that is basically so that we have a copy of the configuration next to the output data named the same way, so that it's pretty foolproof. Hopefully, even if you change your job config, if you leave this parameter in place and run it again, you'll get a copy of whatever job config was run alongside the output, so that hopefully it helps you keep track of basically, what job configuration was used to generate your output data. Anywho, so if that made no sense to you, don't worry too much. The basic point is that just by configuring this text file, you can, define your model and your data and so on. And then when it comes time to actually run your model, if you don't want to write any actual Python code of your own, or not much anyway, it should be pretty easy. So what I'm going to do here actually is, actually I don't need to change directories. I'm just going to go ahead and log into our local Linux machine, well, one of them, which is named Lur, after the character on Futurama, because all of our machines are named after Futurama characters. But you know what? Guess what I should probably do is use the right username for that. Okay. So now we're logged into Lur. I'm going to once again download a copy of the toolbox, just as if I don't have a million copies already on there. But here's a fresh copy of that 0.2b release. Yes, I got a bunch of stuff already in my home directory named this. And I'm going to go in there. This has got all the same files I just unzipped on the Mac, but now we're putting this on this Linux machine of ours. If you look inside here, same stuff as you see back here on the Mac side. And really, if you want to, once you want to run this, so I want to run what I was looking at here is I was looking at the sample job file named sample job file small CNN by subject, CNN meaning convolutional neural network. And the again, you can write your own Python code to run this stuff if you want to, but if you just want to run through a batch file or a job file, you'll just run this main script called DeLINEATE.py using Python. Now, if you want to be able to run that script, you're going to have a machine that's set up to do it. You have to have the backends that we rely on installed. So that means Keras needs to be installed and the stuff that Keras relies on installed. And I'm not going to lie to you folks, it's kind of a pain in the ass. But once you've got all that set up, and we will, be willing to help you with your setup to a certain extent, we have some instructions on our own lab wiki that we're happy to pass along to people. But once you got all your drivers configured for GPU-based processing, all of your CUDA and CUDNN libraries and so on and so forth, and the basic functionality of GPU-based computation is working for you, then when it's all set up with that one-time configuration, it's pretty easy to launch the toolbox. So you just run Python. I have Python version 3 aliased to Py3, but a lot of people would just run Python if that was their current version of Python. You should also be able to run the toolbox with Python 2.7 if you want, but I think Python 3 will generally be the way going forward. We're going to try to keep it compatible as much as we can with both versions, but you never know. So I'm going to, just using Python or Py3, I'm going to run the main delineate script called delineate.py, and I'm going to tell it what job file to run on. So I'm just going to give it sample job file / what was that file called? Sample job file /cnn by subject. So sample job file /cnn by subject. And I'm just going to run that. And we're going to get, it's saying that it's running JSON file number 1 of 1 because you could actually specify multiple jobs to run the command line. It's giving us some warnings that we're using some old versions of stuff. Tells us what GPU device we're using, which is a NVIDIA GeForce 1080 Ti. This stuff all works best on NVIDIA branded GPUs. I'm not sure if there even is support in our backend libraries. That part actually ran pretty quickly. Sometimes that initial step where it generates the model the first time takes a couple of minutes because it has to kind of compile some stuff on the back end. But I might have run this just a minute ago to test it out and make sure it worked for the purposes of video. So whatever it needed to do was already cached, I guess. And what you're going to see basically is this is actually running pretty quickly because it's a small data set just for sample purposes and a simple model. But what it's basically doing here is it's telling you what kind of model you're generating. So this is showing us all the layers that we configured in our batch file. That's something that Keras produces as output, our backend that we rely on. The actual delineate toolbox tells us things like, okay, we're currently in the fourth fold of our loop over our sample attributes. In other words, this is the 5th subject actually because we start counting at 0. Now we're on the 6th subject. So it's going pretty quickly through this iteration over the subjects that we've included, which I think is, I can't remember how many subjects actually are in the sample data set. But anyway, what it does is, it generates this basic neural network, which is showing you kind of what's in that neural network here. And then once it's generated that network, it's going to run it through the training data. This is giving you output on each what we call epoch of the training of the network. Gives you basically it trains with the training data and sort of tests it temporarily or validates it against the validation data set. And what we're seeing here is accuracies against that validation data set, as well as values from our loss function and so on, which if you do any machine learning, that might make sense to you. If not, don't worry about it too much. Anyway, once it gets about as good as it thinks it can get, and again, there's ways for you to specify what that means, it kind of stops generating each model and or stops training each model rather, and then runs that model on the held out test data set so you get good cross-validation, right? Okay, so at this point we've already run through one full iteration, meaning we've gone through all the subjects in our data set once. I'm going to just scroll up and see. Let's see, looks like we had... Looks like we had, 8 subjects in our sample data set, 8 human beings data that we were running over separately. And then you see once we run through all those people, we get a little output message saying that we're on iteration 2. So now we're going to loop through all the subjects, train and test on all the subjects again using, we're going to divvy up the data randomly each time. And so we're going to have, different performances each time, but, this is how we get a good stable estimate of how good our network can do in general doing this stuff. Right, so I think the job file has it configured for us to do 10 iterations of this, but I'm going to stop it early here and just look at the output that we have produced. By the way, yes, it is smart enough to know that if you interrupt a job, if I had specified multiple jobs in the command line, it would have continued on with the next job before it quit entirely. That's basically so if you have, maybe you have a bunch of different models you want to test or a bunch of different ways that you want to do your data analysis, and you see as you're watching it that this one is not up to snuff, you can just hit, Control C to interrupt it, and it'll go on to the next one, and you don't have to kind of stop and restart everything, which is kind of nice. So anyway, now I'm going to go into this sample output directory here and see what's there. There's a little note in here that was already there, but the new stuff that's in here are these output files that I requested in my job configuration to be run. And so I'm just going to actually look at the accuracy summary because that's probably the easiest thing. Just going to copy that and just use the cat command to spit the contents of that file out to the command line. And what you should see here is the performance in a little tab separated value file of how my deep neural net classifier did on everything that we ran it through so far, right? So we only got through all of the first iteration and partially through the second iteration, right? So here's our first iteration there. Here's our 8 subjects. And it looks like, we did, so 33% is chance here, right? And again, this is not a very complex model. We're using like a small subset of our data, so we're not actually expecting this to do all that well. But it looks like we are, pretty consistently above chance with most of our subjects, even, with a lot of kind of caveats that we would not have in real life, because we know just from looking at the whole data set that we can actually do better than this. But, on our held out test data set in the first iteration, we're getting 40% on our first subject, about the same in our second subject. Actually, a little under chance on our third subject. But actually, you can see it's not super consistent between iterations. Again, probably because we have a pretty small sample data set for you here. So it's actually pretty variable, which is one reason why you might want to do multiple iterations. Again, in a bigger data set or a slightly different configuration of the parameters, you might see it being more stable from iteration to iteration. But anyway, so you get a value for each subject, 44%, 52%, so on and so forth. If I had let this thing run through all the way, then I could get an aggregate performance for each subject and then do some kind of statistics on that, compare it to another subject population or another classifier or what have you. You also have your loss value out here, but again, unless you're a machine learning person, you may not care about how to interpret that per se. So that's it for a quick demo now, just to get you a sense of how that might work. And that's pretty much it for now. So thanks for tuning in, and hopefully we'll have more instructions for you soon. Bye-bye.